So in this video we are going to explain the measurements and their statistical analysis. So by the end of the session the students can able to understand how the experimental data is treated statistically and the critical role of a static calibration and traceability in engineering, and how we categorize the measurement standards into primary and secondary categories to minimize the errors in biomedical and automated systems. So first we are going to see about the two distinct categories of the test. One is multiple sample test and single sample test. In a multiple sample test, we take repeated measurements of a single quantity under varying conditions. This means using different instruments, changing the measurement techniques, or having different observers will record the data. So here simply repeating the measurements with the exact same equipment, observer and the procedure does not constitute a multi-sample test. On the other hand, a simple single sample test involves a single measurements or a sequence of measurements taken under completely identical conditions where the only variable changing is time. To truly find the exact absolute value of a measured quantity, we should ideally use as many different procedures, techniques and experimenters as practical to eliminate the bias. So to visualize the statistical data, to visualize this statistical data, look at this histogram representing the measurement of a specific length in millimeters. So on the x-axis we have the measured lengths ranging from 99.7 mm to 100.3 mm. On the y-axis we track the number of observed readings. Notice how the data naturally forms a bell-shaped curve or a normal distribution with a peak frequency of 19 readings hitting exactly at 100 mm. So this gradual representation allows us to easily observe the spread, variance and the central tendency of our sensor data. And here the static performance, calibration process and the instrumentation comparison is given. So all the static performance characteristics of an instrument are actually determined through this calibration process. It is absolutely vital because it gives a very important opportunity to check our instrument against a known standard, that is allowing us to identify inherent errors and also to verify the accuracy. So this calibration is always involves in comparing our target instrument against one of the three things, that is primary standard, secondary standard with higher accuracy, or the instrument of verified known accuracy. So ultimately, all the working instruments used in the daily field measurements must be calibrated against a reference instrument of a higher accuracy grade, ensuring that every measurement can be traced back to a primary standard. So here some of the practical examples and the daily life applications of the measurements is there. So why do we need calibration so badly? Measurement actually is the backbone of science, industry, commerce and daily life, as we know. So we consider the everyday examples. See, considering an healthcare measurements like checking blood pressure or taking body temperature with a clinical thermometer. So checking the time of the day, buying cloth, purchasing groceries or calculating the power bills or through energy meter. Without calibration, the accuracy and reliability of every single one of these measurements could be highly doubtful. So calibration provides the assurance that measuring the device displaying an accurate and reliable value. So deviation is actually the observed reading from the arithmetic mean of the group of readings. So you can see the D1 value, D2 value, finally up to Dn value you can find out. And here we have find out the average deviation, that is defined as the sum of the absolute values of deviations divided by the number of the readings. And here you can see the standard deviation. So in the case of standard deviation, actually this is the infinite number of data where it defined as the square root of the sum of the individual deviations, and it can be shown expressed as below. So however, this number of observations is finite. When number of observations is greater than 20, this will be denoted by the simple O, while it is less than 20, it is denoted by S. And to illustrate how this measurements work in practice means, first, pressure is converted into physical displacement, making the primary transducer. Next, the displacement to convert to the electrical voltage, making the LVDT, that is secondary transducer. So this will demonstrate how multiple stages of the measurement will interact. So these are the applications. And even in the cases of secondary standards, we will observe the standards by the process of serving the basic reference standards, where industrial and commercial measurements laboratory is used. So the individual industry is responsible for maintaining and checking these standards locally against regional references. Periodically, these secondary standards are sent back to the national standard laboratories, and this can be returned to the industry without any official certification varying their exact measured values. So why it is needed? Actually, the need for the calibration is because when first setting the initial calibration level, there are few key factors the managers has to decide, that is manufacturer's official recommendation, frequency and severity of the instrument, environmental influences. So these are the things they have to actually notable. So while measuring the things, they have to check the time of the day, buying cloth for dresses, purchase of groceries, then billing of the consumption through the energy meter. So these are actually needed. And the next one is calibration. So calibration is nothing but meaningless without traceability. So here traceability is the continuous chain of step-by-step comparisons that link our local measuring instrument to the highly accurate natural or international standards. And the next one is the periodicity of the calibration. So periodicity of the calibration is how often should we calibrate. So the periodicity of the calibration is determined by monitoring the calibration data over time to see how much an instrument drifts. When first setting the initial calibration interval, there will be an experienced and a knowledgeable professional value. So they will be seeing about the key factors, that is manufacturer's official recommendation, frequency and severity of the instrument's intended use, and the environmental influences and the required measurement uncertainty. The next one is the primary standards. So these are the absolute high accurate reference standards maintained strictly by the national standard laboratories. They actually represent the fundamental and derived units and are cross compared globally to achieve the world average figure. So primary standards are very few in number, boost the highest possible accuracy and stability over long periods, and are never available for use outside the national labs. So their core function is only to verify and calibrate the secondary standards. And the case of secondary standards, the individual industry is responsible for maintaining and checking these standards locally against the regional references. So periodically these secondary standards are sent back to the national standards laboratories to be calibrated directly against this primary standards. So they are returned to the industry with an official certification validating their exact measured values. And the examples of this transducer indicates the Bourbon tube connected to the LVDT. First it is connected to the Bourbon tube, then to the primary transducer, then displacement is converted to the electrical voltage, and finally this perfectly demonstrates how multiple stages of the measurements interact. And finally it is the applications of the sensor calibration. So in modern engineering, miniature chips integrated multiple numerous sensors are togetherly placed. So if an error is if an error in just one sensor gets undetected, it can degrade the performance of the entire multiple sensor system. Therefore, rigorous calibration is mainly essential to keep the automated and biomedical systems operating with the precision accuracy we depend on. Thank you.